very much, Giovanni. First of all, I'd like to thank our organizer for inviting me, and I will be talking about Magnon Bose-Einstein condensation, and I will present as well as our old results to put everything in proper contents, as well as our new results on spatio-temporal dynamics. And then I would like to acknowledge a very valuable contribution of different people from different groups over the world who participate in these studies. When we are talking about magnons, one should think that magnons are bosons, and in this on this platform, I don't want to speak too much about magnons, but the most important thing is that although that magnons are bosons and they can undergo the Bose-Einstein condensation, and as we will see later, the entire physics of Bose condensation not necessarily needs very low temperatures. This is only for the for atomic condensate, and that was the idea. And although single magnon does not have transverse magnetization, and I would like to thank specifically Sergej who pointed out this point to me recently, the Bose-Einstein condensation is about creation of transverse magnetization, and this is effect of big number of particles. From the general point of view, when we're talking about Bose-Einstein condensation of atoms, there is a famous scenario how the classical gas go to the quantum gas when somebody increase the density of particles or decrease the temperature, and then at some density or at some temperature, this gas undergoes the transition. And there is a condition for this transition, the famous Einstein equation, which defines the critical temperature for given density. But even from this equation, it is clear that you can for any temperature, you can define the critical density. And the point is whether the critical density is too high that you still have a gas, or you already have something which is solid or liquid or even solid. And the main idea or the main criterion of the Bose-Einstein condensation is that the Broglie wavelengths of particle should be about the mean distance between them, which is inversely proportional of the density in the third power. And usually, for atoms, from the thermodynamical point of view, people write in all textbook, you see that chemical potential should be equal 0. This is only true for atoms which have the minimum energy equal 0. In general, the chemical potential for the Bose-Einstein condensation, the chemical potential should correspond to the minimum energy of the particles in our gas. And now we are coming to our magnetic systems. We will be talking about yttrium, iron, garnet. This is ferri, but for us it will be ferromagnetic film. And in these films, the dispersion, and what is important because we are looking for minimum energy, this dispersion is determined by 3 interactions. This is Zeeman interaction, and since this is a single particle interaction, this contribution is independent of wave vector. There is a famous parabola from the exchange interaction. And what is interesting, not so widely known, that for dipole interaction, for such confined geometry, the contribution is rather unusual. The contribution of dipole interaction decreases with increasing wave vectors, and therefore there is a minimum energy which corresponds. First of all, it is not 0, and second, it corresponds to a non-zero wave vector. And one should say that at this minimum energy, the magnon are mainly dipole dominated. The exchange does not play an essential role if one compare the dipole and exchange contribution here. So the idea of such experiments is connected with experimental observation, and as we will see in few minutes, it is necessary to inject additional magnons, because since the magnons are since magnets are they build a gas with a variable number of particles, it means that the chemical potential is equal zero at equilibrium, and minimum energy is not zero. So to observe this effect, one should increase the density of magnets and chemical potential. And we do that using parametric pumping. We did it using parametric pumping. Very recently, we have observed Bose-Einstein condensation by injecting magnets using the spin Hall effect, but I'm not going to talk about that. This is very recent results. And then we observe the distribution of magnets over the spectrum using Brillouin light scattering. Brillouin light scattering is rather, now with the time being, is a very popular technique, and it has something to do with the scattering of light with on creation of quasi-particle with the light. And you see here, this is a brilliant process. A laser photon create a magnon, change its energy and momentum, and usually people use these techniques to determine the dispersion of the quasi-particle, because for a given scattering angle, one has well-defined wave vector of the particle, which is allowed to participate in the process. So by changing the scattering angle, one can walk over the dispersion curve. But in our case, since we are interested in the distribution, we are using wide optic. We integrate the signal over the broad interval of the k vectors, and in that case we obtain a rather broad distribution, and this distribution is nothing else as a population function multiplied by the density of states. Since we know the density of states, the spectrum is known, from this experimental data we can obtain the distribution function, and that's what we are interested in. So the simple experiment which we do is we take our film, and at moment equals 0, we switch on the microwave pumping, and then we observe the distribution of particles of magnets over the energy, and we see that with increasing time, more particles we inject, higher will be the chemical potential. You see that for this blue and olive curve, we can fit this curve using Bose-Einstein statistics, and but at some moment we realize that the distribution goes at low energies. The distribution goes further and grows further, but these are the value which are above the maximum allowed densities. And therefore, we suspect that this is Bose-Einstein condensation. But the first confirmation comes from the fact that if we compare this distribution with distribution at higher energies, this is the same spectrum as we saw before, but I multiply the value by 30, and you see that it's not nice. We can resolve this intensity, and you see that when we go from 300 nanosecond to 500 nanosecond, for example, during these 200 nanoseconds, we inject a huge number of magnets. the population numbers for these states are the same. It means that for all magnets which we injected, or most of them, after some thermalization process, occupy this state. And this is also can be confirmed if we decrease the pumping power. It means we will decrease the flow of additional magnets, and for this low flow, most of them, or some of them, or essential part of them, disappear in the lattice, and you see that we can describe the distribution which we observe at very large time delays by Bose-Einstein statistic, but no transition happens. And that can be also shown if one build a difference between measured value of the magnet's population function and the maximal allowed population function from the Bose-Einstein statistic, and you see we have here a narrow peak. And that was our first publication, where we have shown that we can observe Bose-Einstein condensation at room temperature. And although a few years ago, Sergej published a paper about which has shown theoretically that we create here in this experiment a coherent state, even though there was a very serious questions. For example, from David Snook, who is expert in Bose condensation, who asked the question whether we have really a coherent state, whether we have really thermodynamic state. And later on, another theoreticians, group of theoreticians, even claimed that the condensate we observe cannot be stable, because it is well known that Bose-Einstein condensation happens when particles have repulsive interaction, and it will know up to some time that the magnets have attractive interaction. So after our first publications during a couple of years, there were four important and crucial questions. The first three come from David Snook, and these are: what is the temporal coherence of the condensate? What is the spatial coherence of the condensate? Is the coherence spontaneous? In other words, is the coherent condensate created as a result of thermalization? And from the group of Topitsyn, what is mechanism of stabilization of the condensate? And we spent 10 years in trying to find the answers to this question, and we are proud to say that now that we have found these answers. The first is temporal coherence. And as I said, in our first experiments, we have observed narrow peak, relatively narrow peak. But still, we were sure that its length, its width, is determined by our apparatus function. A couple of years later, we reduced these widths by a factor of 10, and after another several years, we were able to measure real distribution line of the condensates, and here we know that measured line width is really intrinsic line width, because in this experiment the frequency resolution was about 100 hertz, or at least in any case below 1 kilohertz, where we have measured the line width of 800 kilohertz. And I'm very proud to say that this work was done together with Andrei Kirliuk, and these measurements were performed in 9 Magnon. So in any case, we know something we know how coherent, and really it is rather it's very coherent if you keep in mind that the frequency is several gigahertz, so the quality of factor is about 10,000. What is the spatial coherence? Well, we were able to make to perform measurements in k-space, and here is the picture which shows. That show? Oops, it doesn't show. It doesn't show. Okay, it would show how the distribution happens, how thermalization happens, and it should show that the distribution of magnets, which were excited in rather broad contour of K space, then after thermalization, it's focused in very narrow point of K space, which confirm document the high spatial coherence of this condensate. And another experimental confirmation of the spatial coherence were observation of interference between two components of the condensate. As a matter of fact, since I told you that there is a minimum at non-zero k vectors, but due to symmetry, there is not only one such minimum, there are two of them. And so simultaneously, when we create such condensates, we have as a matter of fact, we have two condensates, plus and minus K, and therefore they should interact with each other. And in this work, we were able to show that it's really there is an interference which confirm that this spatial coherence is also rather high. We were able to determine the coherence rate, which is about 40 micrometers. And about spontaneously created thermalization, we have also observed the process, how this condensates is created. Here we have subcritical regime, because if we have very high power, so it's exactly at the critical power, it's a critical density. You see how these magnets, which were created at higher energies, thermalized, and this is really process which has through the many multiple magnon scattering, and we were able to determine thermalization time and compare it with the interaction times of the magnets, and to show that thermalization time is longer than the magnon interaction time, but it is shorter than magnon-phonon interaction time, which shows that we really have quasi-stable thermodynamical state. The same was also obtained with the frequency and the time distribution. This is similar. You can also see that we have created by the parametric pumping a cloud of magnets at rather it's a short around 4 gigahertz, and then we just wait. And then we will see that how first the visible magnets are disappeared, because due to interaction, due to thermalization, some magnets occupy the states which is beyond the sensitivity of brilliant light scattering. But after some time, we see how they come back and then create narrow condensate, which is narrow in frequency, and this is also shows that we have nice coherence thermal. The question is about stability is much more complex. In standard theory, which describe interaction of magnets, which is mainly considered as a self-interaction of magnets, this standard theory predicted that magnets on such a spectrum have rather strong attraction, here and here, and rather weak interaction close to the minimum. And that means that although although the interaction here is weak, but it's still attraction, and therefore the papers of Topitsyn et al. Was correct. They were based on the results of the theory. However, in experiment using the same very sensitive and technique with a very high frequency resolution, we were able to show that if we increase the density of magnets, here you see the frequency of the condensate as a function of pumping power, and this is a critical pumping power, critical density. So here we see how the density, the frequency goes down. This is connected with the fact that the magnets are condensated. But after we reach a critical power, the density goes. Increases and the frequency increases also. It means that the experiment shows that we in fact have a weak repulsion, and in cooperation with Andrei Slavin and Vasil Tiberkevich, we have shown that this repulsion can be connected with interaction, not self-interaction of magnets from the same minimum, but interaction of magnets of two minima, and that might be the explanation. And in the last couple of years, or probably 3 or 4 years, we investigate the thermal and spatial dynamics of magnets, and to do that, we introduce another controlling parameter. We introduce here narrow metallic control line, and by putting in this metallic control line electric current, whether constant or alternative or pulse or in the form of pulses, we can make the chemical potential of the condensate non-uniform. We can locally perturb the magnetic field, and there, on this way, we can perturb the condensate density. And this picture this is from my point of view, it's a very nice picture, shows that if we create in such a control line alternative low frequency megahertz frequency range alternative field, then we create oscillating density of magnets underneath of this control line, and this oscillating density create waves of the density of magnets, which is nothing else as the second sound. Is in a similar way as waves of the density of phonons in superfluid helium create a second sound for phonons. Here we have a second sound for magnets, and this is, I think, a very nice picture. But another story which I'd like to present here is that if we create using this control line a magnetic trap, so the density, the intensity of field is reduced. This is a trap for condensate, and the condensate density should increase. And this is really happens. Here you see what happens again. We change the pumping power, and this is a critical value. And for without any current in the control line, we have such changes with the time, which tells us how the condensate density depends on the power. But one can see that if we change the chemical potential locally, and if we create a trap, the density of condensate in the trap increased dramatically. Note that it's a logarithmic scale. So we have something like that. The condensate has a maximum in the trap, and vice versa. If we create a potential heel, the density goes down, and we have here a depletion. And this is a very interesting phenomena, which tells us that we have something to do with lateral flow of condensate, because as I will show here, as you see here, we show that normalized condensed density with one will be unperturbed condensed density, and you see for the trap we have increase of the density in the trap, but outside the trap we have a long area, a large area where the density is decreases. It means it's obviously that we have here something to do with the transfer of condensate from here to here. And vice versa, if we have a potential here, we have it smaller here, but outside the heel, we have an increased density. So it means that we observe here the flow of condensate in the lateral dimension, and we described it using some kind of, we started with Gross-Pitaevsky equation, modified by taking into account dissipation flow, and we were able to describe these curves using results of this equation. And what is interesting, this is, I have already said. What is interesting that to describe that we have to introduce the interaction between the particles, and this interaction is repulsive. And that is very interesting. Moreover, what is also interesting from this transport equation, we can determine the mobility of the of magnets in the condensate, and the corresponding relaxation time, which you can calculate from the mobility, is huge. It's very long. It's 10 microseconds with respect to 100 nanosecond of the lifetime of the condensate if you switch off the pumping. And this is shown in this experiment. What we have done, we create the condensate in the trap, and then we switch off the pumping. What it happens, of course, what happens is that the density goes down. But if you normalize the density and look how the width of the condensate in the trap is varying, you see that with decreasing the density with the time, the width goes down. And this is also can be shown on the trace if you take in one point and trace and look how the density goes with the time. But this picture already tells us that we have a repulsion, because for higher density, the magnets they repulse each other from the trap, and as soon as we decrease the density, when this repulsion becomes negligible, everything goes back to the initial width which is determined by the trap. And finally, what I'd like to say about this spatio-temporal dynamics, I think I am already almost used all my time. If we switch on the trap abruptly and look what happens with the density of the condensate in the trap, we observe oscillation. What you see here, different curves, density of condensate density as a function of time, normalized by the width of the depth of the trap. For you see that you have different depths of the trap, and what we see that we have monotonic increase, and this is we know that in the trap the density is larger than outside the trap, and since these three curves on this scale, on this coordinate, are equivalent, one can say that the time of monotonic exponential growth is inverse proportional to 1/h. We see in addition frequency oscillations, and they are proportional square root of the depth, and we see that the damping of oscillations is more or less independent of the of the trap width depth. So I see that the chairman is already then, therefore I skip. And before I make my conclusion, I would like to say whatever I said at the end of each my talk. Since couple of years, we see attempts to describe properties of dipole spin waves using spin current. And my statement is that since dipole interactions, not my statement, I just repeat the statement then done by Blombergen in 1959, that since the spin angular momentum does not commute with the dipole interaction, the dipole interaction does not conserve spin, since the spin is not conserved, you cannot use the concept of spin current to describe spin dynamics. And there is a lot of example where apparently this model fails. Nevertheless, we have in some papers and some conference talks that people try to do that, and I'm very sorry about that. Okay, I am now done. During this relatively short lectures, I have shown you that since the discovery of room temperature Bose-Einstein condensation opened several fundamental questions. And it takes us several years to answer them, and we are very proud about that. And we have now know what are the coherence property of the condensate. We know that we have second sound. We introduce a special, a new dimensionality investigation of condensate by creating inhomogeneous potential and observe some kind of flow of condensate which behave itself as a Magnon fluid. And last but not least, since magnets are in condensate and in many cases are dipole dominated, the attempts to describe the condensate and another dipole dominated magnets using spin current approach are really questionable. Thank you very much for your attention. I'm done.